All right, so the idea of modes. If you just have, let's say, a particle, let's say a hydrogen atom, or let's say helium atom, because hydrogen is not going to come in individual atoms. If you just have a single solitary hydrogen or helium atom, and let's say it's in gas phase. If we're talking about modes, first of all, what do we mean by a mode? What is a mode? It's related to types of energy, yeah. I wouldn't say it's just a type of energy because we wouldn't just say there's a kinetic energy mode and a potential energy mode. But it's certainly a way a particle can have energy. And yeah, it has to do with how many directions it can be in also. Yeah, we often think of it as like a box or a container for holding energy, that there's certain ways the particle can have energy. So kinetic energy and potential energy would be possible types of energy. But also we care about direction as well. The idea here is we're talking about energy types or ways to have energy that are independent of each other. And mathematically, when we talk about independent, we're largely talking about direction. Like for instance, if you got motion in this direction and also more motion in this direction, same direction, that's not really independent ways to have energy. It's essentially the same way to have energy. Or in more dimensions, let's say you're talking about like travel in this direction and also travel in this direction. Those count as two independent directions. There's no way to make one of them out of the other. But then if you talk about travel in this direction, that's just a combination of some amount in one direction and some amount in the other direction. That is, you can split that up into some amount in the first direction we already talked about and some amount in the second direction we already talked about. So that diagonal doesn't count as a separate direction. And this is really ultimately all about dimensions. How many different dimensions in our own universe can a particle move in? Yeah, it can move in 3 dimensions. You can have the particle moving up and down. You can have a particle moving left and right. That counts as an independent set of directions because there's no way to make left and right out of up and down motion. And also out of the page and into the page, which is kind of difficult to draw on just a flat screen. But if you imagine that diagonal is out of the page and into the page, or out of the screen and into the screen, that's 3 dimensions worth of motion. And again, if you're talking about some sort of diagonal, let's say you're going in this direction, that direction can be expressed as, let's say, some amount in the x direction and some amount in the z direction. So we don't need a separate dimension to account for those diagonals. Any particle in our own universe can move in 3 dimensions, or possibly fewer than 3. There might be some restrictions on its motion, so it can only move along a flat plane or only move in a straight line, for instance. But without any restrictions, we would assume a particle can move in 3 dimensions. And that means it has 3 ways to have kinetic energy. It could be moving in the x direction, moving in the y direction, and moving in the z direction. So we would say it has 3 modes of translational kinetic energy. So it's got 3 translational kinetic energy modes because it's able to move in 3 dimensions. And generally, we should expect that to be true for any particle. Any particle that can move in 3 dimensions, unless specified otherwise. Would this helium atom have any potential energy? Is it interacting with any other particles? No. And how do we know? Why would we expect this atom to not be interacting with any other particles? Right.
Because it's a monatomic gas?
Yeah, it's a gas. And in this case, yes, it is monoatomic. But even if it were polyatomic, we would expect like this molecule to be not interacting with other molecules because they're so far apart from each other. So we would expect this to have no potential energy because there's nothing to interact with. Potential energy is all about interaction. So that means this one atom would have only the 3 translational kinetic energy modes, and that's it. However, we're usually not talking about just one single atom. Usually we'd be talking about a large cluster. Like for example, let's say we had 5 moles. If we wanted to figure out the total number of modes there, what would we have to do? If we wanted to know this sample has how many modes? Yeah, first of all, Avogadro's number, right? We know the number of modes for one particle, that's just 3 modes per particle. Multiplied by Avogadro's number, that'll get us the total number of modes in 1 mole, but how many moles do we have? Right, we then have to multiply by 5. So 3 modes per particle times Avogadro's number tells us the number of modes in 1 mole of particles times 5 to give us the number of modes in 5 moles. So 5 Na times 3, in other words, 15 Na modes. And if we needed to, we could substitute in Avogadro's number 6 times 10 to the 23rd and get the number of modes as, what would that be? 6 times 15 would be 90, so 9 times 10 to the 24th modes. So that would be the total number of modes in this entire sample. That is the total number of ways this sample can have energy. Any questions on that so far? And probably the most important thing about modes, once we know how many modes there are, what should we, I mean, we were saying all along that a mode is a way for the particle to have energy, essentially like almost like a container that holds energy for the particle. This sample has 9 times 10 to the 24th ways to have energy. How do we figure out how much energy each of those modes contains? Or what would you expect about the distribution of energy here? If all of these modes have some energy, would you expect any of those modes to have more energy or less energy than all the other modes? Yeah, the energy should be divided up equally. Assuming what? What has to be true in order to ensure that energy is divided equally? Or what does it mean for energy to be divided equally? How would we observe that macroscopically? Yeah, the temp has to be the same, the temperature. If the whole sample is all at the same temperature, then that means the energy per mode is the same everywhere. This is usually called the equal partition theorem. That if the temperature is the same everywhere, otherwise known as thermal equilibrium, then we can expect all the available mode, or we can expect the thermal energy to be distributed evenly amongst all available modes. And we say all available modes because it's sometimes possible that some modes aren't there or aren't active. But in general, if you have some certain number of modes and everything's at thermal equilibrium, all at the same temperature, then we can expect the thermal energy to be distributed evenly amongst all the modes. And this is kind of an on average thing. In reality, if you were able to use some sort of hyper-powered energy microscope to look at the individual modes, you might find that right now this particle is moving a little bit faster than this particle, or this particle is moving more in the X direction than the Z direction. But on average, all the modes should have about the same amount of energy if the temperature is uniform. In fact, this is essentially what temperature means. Same temperature means same energy per mode. So energy per mode depends only on temperature. Or to put it another way, temperature is essentially a way of measuring the energy per mode. And this doesn't depend on what type of substance it is or even what type of mode it is. If you have a sample of some substance at 30 degrees Celsius and another sample of a different substance somewhere else that also is at 30 degrees Celsius, those being the same temperature means they have the same energy per mode. So energy per mode should equal something about temperature. In fact, it should be proportional. If you have, let's say, a sample at a certain temperature in kelvins and another sample that's got 3 times the temperature, it's also going to have 3 times the energy per mode. Temperature and energy per mode should be proportional, which means energy per mode equals some constant times temperature. And that constant happens to be Boltzmann's constant over 2, half of Boltzmann's constant. So we can use this idea that the energy per mode is half of Boltzmann's constant times the temperature to calculate the energy of one mode. Any questions on that so far? And by the way, this Boltzmann's constant over 2, you could almost think of as like a conversion factor. This is just a constant for converting between temperature in kelvins versus energy per mode in joules. So I think that's probably the best way of thinking about this constant. Kb over 2, Boltzmann's constant over 2, is a conversion factor that converts from kelvins to joules per mode. 2 substances at the same temperature, yeah, if they've got the same temperature, then they have the same energy per mode. So more modes directly translates to more thermal energy. For instance, in this case, for the helium atom, or for the 5 moles of helium, if we wanted to find the total thermal energy, what would we do here? If we know it's got 15 times Avogadro's number of modes, and we know the energy per mode, how would we figure out the total thermal energy of that whole sample? Yeah, we can just multiply the energy per mode, Kb over 2 times temperature, times the number of modes, 15 times Avogadro's number. Because we know that each one of those modes has that tiny amount of energy. So number of modes total times energy per mode. Modes and modes cancel out, so you just get total energy. So we get number of modes total, that was 15 times Avogadro's number, times energy per mode, Kb over 2, Boltzmann's constant over 2, times the temperature. This should tell us the thermal energy of the whole sample. 15 over 2 would be 7.5 times Boltzmann's constant times Avogadro's number times the temperature. So if we know the temperature and we can fill in 6 times 10 to the 23rd for Avogadro's number, and Boltzmann's constant I think is 1.3 times 10 to the negative 23rd joules per Kelvin mole, something like that. So multiply, or joules per Kelvin, I guess. Multiply those together and that'll give us the total thermal energy. Any questions on that so far? Also a very useful abbreviation. In many situations when we do this, we end up with a Boltzmann's constant times Avogadro's number, because we're multiplying the energy per mode, which includes this very tiny number, Boltzmann's constant, and the number of molecules. Since we're usually describing this in number of moles, number of molecules is going to be usually including, not always, but usually including Avogadro's number, which is enormous. So we've got a very tiny number times a very large number. And those end up balancing out to a much more manageable number. And this shows up often enough that it has its own abbreviation. Anytime you've got Boltzmann's constant times Avogadro's number, anyone know what that's usually called? Yeah. That's R. That's the ideal gas constant. And this is the same R, the same constant that shows up in the ideal gas equation, PV equals nRT, which is why it's called the ideal gas constant. And a very useful way of thinking of this R, Kb is talking about the energy of one mode as it relates to temperature. If you multiply by Avogadro's number, that scales it up, because Avogadro's number describes, what does Avogadro's number mean? What's that talking about? Like Avogadro's number, yeah, it's the number of particles in 1 mole. So Boltzmann's constant is talking about the energy of individual molecules or individual atoms. Multiplying by Avogadro's number scales it up. So you're now talking about the energy of entire moles instead of the energy of individual molecules. So R, the ideal gas constant, basically serves the same role as Boltzmann's constant in terms of energy conversion, but when we're talking about entire moles rather than individual molecules. And that makes for a very useful conversion. We can replace Kb times Na with just R. So thermal energy is 7.5 times R times temperature. And R is much more convenient to work with. It's about, I think it's 8.3? It's about 8.31 joules per Kelvin mole. So you can fill that in, multiply by, in this case, 7.5, and then multiply by the temperature of the sample, and that'll tell you the thermal energy. So this is a very convenient way of calculating the thermal energy, not based on some property of the substance that you look up in a data table, but instead based on the behavior of the individual particles. So this is tying together a macroscopic quantity you can directly measure, the temperature, versus microscopic behavior of the individual molecules. And this is kind of a running theme. As we're looking at both bond energy and thermal energy, we're looking into how does the individual behavior of the molecules microscopically influence and cause the macroscopic behavior that we actually observe in terms of phase change and temperature change. Any questions on that so far? Then let's try modifying this a bit. Let's say instead of a gas, let's say we have a liquid. Let's say we cool off the helium so cold that it becomes liquefied. It condenses into a liquid. So let's say we're now talking about liquid helium. What difference would that make to our calculations other than just using a lower number for temperature? What's probably the biggest difference between liquid and gas at the atomic level?
On how the particles are interacting with each other, because in a solid liquid, the particles, they're bonded, I think, compared to a gas where they're just floating around.
Exactly. In a gas, the particles are so far apart, we expect they don't interact with each other at all. But in a liquid, the particles are much closer together. They're still pretty free to move compared to a solid. They're able to move around. They're only partly bonded, but they are interacting with each other. And if they're interacting with each other, they can still move. So we still expect the 3 translational modes. Even if they're not like freely moving, they're just sort of vibrating in place mostly. That still counts as motion. They can still vibrate in 3 dimensions. But they can also interact with each other. So what other type of energy should we expect? Yeah, we've also got potential energy. There's the translational kinetic energy because they can move. And there's also potential energy modes. And I usually call these external vibrational potential energy modes. Internal vibrational, we're usually talking about atoms inside a molecule interacting with each other. External vibrational modes, we're talking about molecules or atoms interacting with other molecules or atoms in the same substance. And how many dimensions can it interact in? Yeah, it can interact in 3 dimensions. It can interact with neighbors to its left and right. It can interact with neighbors in front and behind. It can interact with neighbors above and below. So that's 3 dimensions worth of interacting. And note this does not depend, this is not about how many bonds. This may be connected to maybe a few bonds, maybe a lot of bonds, maybe up to 12 nearest neighbor bonds if it's like a closely bonded solid. But the thing is, this isn't about number of bonds. This is about number of dimensions. No matter how many bonds this is involved in, it's still interacting with its neighbors in 3 dimensions. So it's going to have 3 external vibrational potential energy modes. So 3 modes of kinetic energy because it can move in 3 dimensions, and 3 modes of potential energy because it can interact with its neighbors in 3 dimensions. So it looks like that makes for a total of 6 modes. And of course, then we'd have to modify our subsequent calculations as well. Instead of 3 modes per particle times 5 times Avogadro's number, we'd have 6 modes per particle times 5 times Avogadro's number. So instead of using 5, we would use, or instead of using 3, we would use 6 modes per particle. And then carry out the rest of the calculations from there. So that would change the result. Could have rotational modes if it were polyatomic. In this case, it's monoatomic, so there's no rotation. It's like the idea is if you just have a particle that's just one single atom, a single atom is basically just a single point. So if you have, let's say you just got a tiny monoatomic sphere. If you rotate this, nothing's really changing. It's still just a sphere. Nothing's really moving as you rotate it. So that means that we can ignore rotation for individual atoms. If you're talking about a molecule, though, a polyatomic molecule, then rotation comes into play. So for monoatomic, you would just have the 3 translational modes because it can move. And if it's a solid or liquid, you would also have 3 vibrational potential energy modes. I'm including that as the translational kinetic energy modes. Some people list it as vibrational kinetic energy instead of translational kinetic energy. I don't really see much of a difference there because in both cases, it's just in motion. So if you want, you could call this vibrational kinetic energy, but it's still in motion. So I would just call it translational kinetic energy. But you probably want to ask your instructor to see which words are expected on an answer. But it's still, formally, it is still translational because the molecule or the particles are in motion. They're just not moving very far because they're vibrating back and forth. Any other questions on the monoatomic substance so far? I guess what I would say there is it regardless of what you call the kinetic energy, whether you call it translational or vibrational, this monoatomic liquid has 3 modes of kinetic energy, whatever type you want to call it, and 3 modes of potential energy. So a total of 6 modes per particle. And note that half of those are kinetic energy and half of them are potential energy. So for a liquid or solid, the thermal energy is half kinetic and half potential, because half of those modes were translational kinetic energy and the other half were potential energy. Whereas for a monoatomic gas, they were all kinetic energy. So for a gas, all the thermal energy is kinetic energy. Any other questions on monoatomic before we take a look at more complicated molecules? Then let's try the same approach for, let's say, diatomic gas. Let's say hydrogen. Hydrogen being diatomic is going to have 2 atoms bound together. And let's say it's in its gas phase. So we don't have to worry about interaction with other molecules. How many different dimensions can this molecule move in? Yeah, it can still move in 3 dimensions. So we're going to have translational modes. 3. It can move in 3 dimensions. And there's no interaction with its neighbors. So that means we don't need to worry about any potential energy of interacting with neighbors. But how else can it move other than translation? That's going to become important here. Yeah, if it's not just a single particle anymore, rotation becomes important. Once again, a single particle, if you rotate it, nothing really changes. But if you now have a diatomic molecule, if you rotate this, that's actually motion. It has kinetic energy as a result of its rotation. And how many dimensions can it rotate in? Yeah, why only 2 instead of 3 in this case? Right. The fact that it's linear in shape limits it because it has an axis of symmetry. If you rotate around, let's say, this axis, this rotation, I don't know if you can see that clearly, this rotation counts as a rotation that's meaningful. Or if you rotate it around this axis, this rotation also counts as a rotation that's meaningful. But if you try to rotate it around its own axis of symmetry, this rotation doesn't actually change anything. It doesn't involve motion of the parts of the molecule. So rotation around its own axis of symmetry does not count as any sort of rotational kinetic energy, which means that this linear shaped molecule only has 2 rotational modes. If it was nonlinear, then it would have more. For instance, if you had, let's say, a triatomic molecule with a bend in it, in that case, there's no axis of symmetry in that sort of way. You can rotate it like this, you can rotate it like this, and you can rotate it like this. All 3 of those rotations count as distinct rotations. So if it's nonlinear in shape, if it's got any sort of bend or anything off that line, then it's going to have 3 rotational modes. If it's linear in shape, even if it's more than 2 atoms, as long as all those atoms are in a straight line, rotation along its axis of symmetry doesn't count. So 2 rotational modes if it's linear, 3 rotational modes if it's nonlinear, and no rotational modes if it's monoatomic. And we're assuming this is in gas phase, so it's not interacting with any other molecules. But this can still have potential energy, because what sort of interaction could be happening? Yeah, we could have vibrational kinetic energy going on inside the molecule itself. Keep in mind, we're treating the atomic bond almost as if it's like a tiny invisible spring. So you could have the atoms in the molecule getting closer to each other, getting farther from each other, getting closer to each other, getting farther from each other. Essentially like the Lennard-Jones potential energy stuff we were looking at earlier, the oscillation of these molecules. Which means that the atoms have potential energy because they're interacting with each other within the molecule. And they also have kinetic energy because they're moving along that bond within the molecule. But if you just consider within the molecule, how many dimensions is that vibration occurring in? Yeah, this vibration within the molecule is essentially just one-dimensional because they can be vibrating in and out. That counts as vibration. But the thing is, if they're like, let's say one's moving up and one's moving down, if you've got one atom moving up and the other moving down, the molecule is not vibrating, it's rotating. And we already counted rotation. Or let's say they're both moving up. That's not vibration, that's translational motion. And we already counted that as well. So if we ignore all the types of motion we've already included, the only one left is both moving in, both moving out. So that's the one dimension of vibrational motion. However, along that one dimension, they could have kinetic and potential energy. So that actually counts as 2 modes. And we would call this internal vibrational modes. There's 2, of which one is kinetic and one is potential along that one dimension of bond. So in general, a diatomic molecule could have 2 internal vibrational modes, one kinetic and one potential. Any questions on that so far? So that's pretty much all the types of modes we need to consider. There's the kinetic energy modes of motion, translational, or if it's a solid or liquid, you might call that vibrational. The internal vibrational modes, yeah, you can treat the particles as if they're the atoms within the molecules as if they're connected by a tiny invisible spring. So if you had like 2 objects on a string bouncing back and forth, they'd have kinetic energy because they're in motion and potential energy because they're connected by the spring. They're interacting. If it's triatomic, it gets more complicated because you've got motion along motion of each atom in relation to both of the other atoms. So if it's triatomic or larger, it's not quite as straightforward as just one kinetic and one potential energy mode. It's not even as simple as a certain number per bond. Typically, what you would do instead for polyatomic molecules, like let's say you have a cluster or a molecule, not a cluster, but just one molecule that's, let's say 5 atoms in sort of a zigzag shape. So if you've got 5 atoms in sort of a zigzag shape, a pentatomic molecule, a nonlinear 5-atom molecule. If we wanted to figure out how many modes that had, and let's assume it's a gas, so we don't have to worry about interacting with other molecules, we can focus on just this one. A very useful way of figuring out how many modes to expect there. First of all, if we just treat the atoms separately, if we just treat the atoms individually, how many modes would you expect each individual atom to have? If you ignore the bonds and just look at one atom in isolation, how many kinetic energy bonds or modes would you expect that to have? Yeah, each one is expected to have 3 kinetic energy modes. So if we've got 5 atoms, right, we should expect 15 kinetic energy modes. We expect 15 kinetic energy modes for the whole molecule. So that's how many we should expect based on the behavior of the individual atoms. But let's put that aside for a moment and count up how many we have so far. Looking at the molecule as a whole, if we just, ignoring the individual atoms and just looking at this as one big molecular shape. How many modes would you expect just by considering the whole molecule? If we listed out the modes we would expect, how many modes would you, or what modes would you expect this to have? Kinetic energy, and it would have the vibrational potential energy, but let's ignore that for the moment. Just looking at kinetic energy, what types of kinetic energy would you expect? Yeah, we expect 3 translational modes. And also, what else? Some number of rotational kinetic energy. And specifically, if it's nonlinear, how many rotational modes would you expect? How many dimensions can it rotate in? Yeah, it can rotate in 3 dimensions because it's nonlinear, so all the rotational modes are active. And possibly some internal vibrational modes, but we don't know how to calculate those yet. But just based on what we've seen so far, looking at the whole molecule, if you imagine the whole molecule is one rigid object, it can move in 3 dimensions, it can rotate in 3 dimensions. That's how many kinetic energy modes so far. If we look at just the whole molecule and ignore what's going on inside, how many translation or kinetic energy modes? Yeah, we've got 6 kinetic energy modes so far. If we ignore the individual atoms and just treat the whole molecule as one solid block, we would expect 6 kinetic energy modes. Or we've accounted for 6 modes so far. But based on the individual atoms, we should expect 15 kinetic energy modes. So we expect 15 kinetic energy modes based on the 5 atoms. We've counted 6 so far. How many are left over that are unaccounted for? A lot more than 4, because we have, yeah, it should be 9, because we were expecting 15 to start with. Right, we've already counted 6. So there are 9 leftover modes we haven't found yet. Of the 15 modes we should expect based on the atomic behavior, we've accounted for 6 based on the whole molecule behavior. We still have 9 modes unaccounted for. And yeah, that is exactly from 15 minus 6. 15 that we expect based on the behavior of the atoms, minus 6 that we've accounted based on the behavior of the whole molecule, leaves 9 left over. So what would you expect those 9 leftover modes to be? What kind of kinetic energy is that talking about? Exactly. These are the vibrational kinetic energy modes. Specifically the internal vibration, the atoms moving within the molecule. Because there's 15 ways for the molecule, 15 ways for the individual atoms to be in motion. We've already counted 6 of those ways as the whole molecule moving and the whole molecule rotating. The other 9 ways the atoms could be moving are just a jumble of vibration within the molecule. So there's 3 ways the molecule could be moving, 3 ways the molecule could be rotating, and in 9 ways the molecule could be vibrating as a jumble of atoms inside. But that's 9 modes of vibrational kinetic energy. What other energy should we expect based on the behavior of these bonds as acting like springs? Think about kinetic energy, yeah, and also potential energy. And right, that should also be 9 modes of vibrational potential energy, because we expect the kinetic and potential energy of vibration to be paired like that, in the sense that a spring, any spring system has kinetic energy and potential energy. 9 modes of vibrational kinetic energy essentially means this is acting like 9 springs or 9 mass spring systems. So with 9 modes of vibrational kinetic energy, there's also 9 modes of vibrational potential energy for a total of 18 vibrational modes. So I think that should do it. This molecule is going to have 6 kinetic energy modes, specifically 3 translational and 3 rotational, plus 18 vibrational modes. 3 translational modes, 3 rotational modes, and 18 vibrational modes. Or in total, 3 plus 3 plus 18 would be 24. So each one of these molecules would have 24 modes. Any questions on that so far? And we can actually generalize this instead. Suppose instead of having 5 atoms, let's say we had n atoms. So let's say instead of having 5 atoms, we had n atoms, where n is just some number of atoms in the molecule. If we have n atoms, how many kinetic energy modes would we expect? Yeah, linear versus nonlinear, the shape of the molecule. Let's assume it's still nonlinear. So let's still assume it's nonlinear. It's just n atoms instead of 5 atoms. So for the moment, we're still assuming nonlinear in shape. But with n atoms, how many kinetic energy modes would you expect from n atoms? Yeah, instead of 15, we would expect 3 times n, where n is the number of atoms in the molecule. Not the total number of atoms in the whole system, just the number of atoms in this one molecule. So we should expect 3n modes. And as before, we would expect the whole molecule to have 3 translational modes, and if it's nonlinear, 3 rotational modes. So if you expect 3n modes in total, and you've already accounted for 6 of them, how many modes are left over unaccounted for? Instead of 9, we would expect how many unaccounted modes? Exactly, 3n minus 6. So the unknown modes, the unaccounted for modes, are going to be 3n minus 6. because we expect 3n in total from the atom's behavior alone, minus 6 that we've already counted, so 3n minus 6 unaccounted for modes. Those are the vibrational kinetic energy modes, and therefore, how many vibrational potential energy modes would we expect? Yeah, it should be also 3n minus 6, right? The same. So we essentially just double this. We've got 3n minus 6 vibrational kinetic energy modes. We double that because we have the same number of potential energy modes. So 3n minus 6 doubles would be 6n minus 12. So we should expect 6n minus 12 vibrational modes. Combine that with the 6 kinetic energy modes we already counted, this translational and rotational. We got 3 translational, 3 rotational, and now for this n atomic molecule, we have 6n minus 12 vibrational modes. Add those all up, 3 plus 3 plus 6n minus 12, and what do we get instead of 24? The 6n minus 12 vibrational modes plus the 6 modes we already counted, what do we get? Yeah, 6n minus 6. So this nonlinear molecule consisting of n atoms, we would expect to have 6n minus 6 modes. So we can use that as a formula. Anytime you've got a nonlinear molecule, if all the modes are active, and assuming it's a gas, then it should have 6n minus 6 modes. Alternatively, if it was linear, what would we have to do differently? What would be the only difference there if it was linear in shape? What would be the only part of this whole thing that changes? Not quite 5n minus 6. We'd still be multiplying n times 6 because of the 3n minus 6 doubled. But yeah, the rotational modes, that would mean 5 kinetic energy modes already counted. So we'd still have 3n modes expected from the atoms, but we'd be subtracting 5 instead of 6. So instead of subtracting 3n expected minus 6 already counted, we'd be taking 3n already counted, or 3n expected minus 5 already counted. So 3n minus 5 vibrational kinetic energy modes from 3n that we expect minus 5 that we've already counted. Double that because there's also potential energy modes, so 6n minus 10. Add the 5 modes we'd already counted, we get, yeah, 6n minus 5 should work. So we can use that as a formula as well. 6n minus 5 modes total for a linear shaped molecule. In fact, we could even try applying that to the hydrogen gas we already looked at. Hydrogen gas, what's n for the hydrogen gas? That is, how many atoms are in that molecule? Right, n equals 2. So if we use the formula, should we use 6n minus 5 or 6n minus 6 here? Is that linear or nonlinear? Yeah, linear, so we use 6n minus 5. 6n minus 5 modes. We plug in 2 for n. 6 times 2 minus 5. That's 12 minus 5, which is 7. And if you compare that to what we already counted up here, we've got 3 plus 2 more plus 2 more. That's our 7 modes. So by counting the modes, we get 7, but we also get 7 predicted by this formula. So the formula we just created matches up with what we got by counting the modes for hydrogen. And for larger molecules, of course, it becomes much more complicated to actually count all those internal vibrational modes. but the formula 6n minus 5 or 6n minus 6 should predict how many modes to expect in total for one molecule. And those aren't always active. If it's at low temperatures, some of those modes will be frozen out. It requires a certain amount of minimum energy to vibrate. It also requires a certain amount of minimum energy to rotate. So at very cold temperatures, these won't all be active. But if the temperature is high enough that all the modes are active, the 6n minus 6 or 6n minus 5 formulas will predict how many modes to expect. Any other questions on modes? You're welcome. And we can look at some more examples next time. Feel free to contact me online if you want to request any more examples or topics to look at, and I will see you then.